Calculus 2. Integration techniques. In this chapter we will look at several integration techniques including integration by parts, integrals involving trig functions, trig substitutions, and partial fractions. We will also look at improper integrals including using the comparison test for convergence/divergence of improper integrals. Integration by parts. In this section we will be looking at integration by parts. Of all the techniques we'll be looking at in this class, this is the technique that students are most likely to run into down the road in other classes. We also give a derivation of the integration by parts formula. Integrals involving trig functions. In this section we look at integrals that involve trig functions. In particular, we concentrate integrating products of sines and cosines as well as products of secants and tangents. We will also briefly look at how to modify the work for products of these trig functions for some quotients of trig functions. Trig substitutions. In this section we will look at integrals that require the use of a substitutions involving trig functions and how they can be used to simplify certain integrals. Partial fractions. In this section we will use partial fractions to rewrite integrands into a form that will allow us to do integrals involving some rational functions. Integrals involving roots. In this section we will take a look at a substitution that can, on occasion, be used with integrals involving roots. Integrals involving quadratics. In this section we are going to look at some integrals that involve quadratics for which the previous techniques won't work right away. In some cases, manipulation of the quadratic needs to be done before we can do the integral. We will see several cases where this is needed in this section. Integration strategy. In this section we give a general set of guidelines for determining how to evaluate an integral. The guidelines give here involve a mix of both Calculus 1 and Calculus 2 techniques to be as general as possible. Also note that there really isn't one set of guidelines that will always work, and so you always need to be flexible in following this set of guidelines. Improper integrals. In this section we will look at integrals with infinite intervals of integration and integrals with discontinuous integrands in this section. Collectively, they are called improper integrals, and as we will see they may or may not have a finite, i.e., not infinite, value. Determining if they have finite values will, in fact, be one of the major topics of this section. Comparison test for improper integrals. It will not always be possible to evaluate improper integrals, and yet we still need to determine if they converge or diverge, i.e., if they have a finite value or not. So, in this section we will use the comparison test to determine if improper integrals converge or diverge. Approximating definite integrals. In this section we will look at several fairly simple methods of approximating the value of a definite integral. It is not possible to evaluate every definite integral, i.e., because it is not possible to do the indefinite integral, and yet we may need to know the value of the definite integral anyway. These methods allow us to at least get an approximate value, which may be enough in a lot of cases. Applications of integrals. In this chapter we'll take a look at a few applications of integrals. We will look at determining the arc length of a curve, the surface area of a solid of revolution, the center of mass of a region bounded by two curves, the hydrostatic force/pressure on a plate submerged in water, and a quick look at computing the mean of a probability density function. The applications given here tend to result in integrals that are typically covered in a Calculus 2 course. Arc length. In this section we'll determine the length of a curve over a given interval. Surface area. In this section we'll determine the surface area of a solid of revolution, i.e., a solid obtained by rotating a region bounded by two curves about a vertical or horizontal axis. This center of mass. In this section we will determine the center of mass or centroid of a thin plate where the plate can be described as a region bounded by two curves, one of which may the x or g y-axis. Hydrostatic pressure and force. In this section we'll determine the hydrostatic pressure and force on a vertical plate submerged in water. The plates used in the examples can all be described as regions bounded by one or more curves/lines. Probability. Many quantities can be described with probability density functions. For example, the length of time a person waits in line at a checkout counter or the lifespan of a light bulb. None of these quantities are fixed values and will depend on a variety of factors. In this section we will look at probability density functions and computing the mean, think average wait in line or average lifespan of a light bulb, of a probability density function. Parametric equations and polar coordinates. In this chapter, we will introduce the ideas of parametric equations and polar coordinates. We will also look at many of the basic calculus ideas, tangent lines, area, arc length, and surface area, in terms of these two ideas. Parametric equations and curves. In this section, we will introduce parametric equations and parametric curves, i.e., graphs of parametric equations. We will graph several sets of parametric equations and discuss how to eliminate the parameter to get an algebraic equation, which will often help with the graphing process. Polar coordinates. In this section, we will introduce polar coordinates, an alternative coordinate system to the normal Cartesian/rectangular coordinate system. We will derive formulas to convert between polar and Cartesian coordinate systems.